Hey guys, thank you for joining us. Good morning. I'm Daniel Lazarev. I'm an AI security researcher at Wiz.
Hello everyone, I'm Erez Harush. I'm leading the AI research at Wiz. And today we're going to talk about how we use a small language model to enhance our secret detection engine. So let's start with some motivation. Stolen credentials are still one of the most common attack vectors. We see it in 1 to 3 of all the breaches. And we can find stolen credentials in many places. For example, public repositories that you mistakenly commit like a secret. The second thing is misconfigure or vulnerable cloud resources. For example, a public bucket that you store sensitive data or credentials that doesn't supposed to be public. And the third thing is compromised workstation. So an attacker can get access to a workstation, and there they can find probably credentials storing in some files.
According to our research, 86% of organizations have at least one repository with secrets inside. But the more concerning number is that the organizations with secrets in their open source and public repositories. When looking at cloud keys, we are particularly interested in the secrets attackers can use to perform lateral movement in the cloud. This number is likely even higher for the general population, since our data is drawn from organizations that are protected only by us. So, what's on the agenda today?
So we're going to start with the current solution of secret detection and check if there are enough. Then we're going to talk about generating data using LLM agent.
Then we're going to dive into fine-tuning small language models and also talk about evaluation and metrics.
We're going to finish with some key takeaways. So let's start with understand the challenge of secret detection in files. We're living in a world that we have more and more third-party integrations, and actually there is more and more API keys and tokens and service accounts that we need to integrate with these third-party integrations. Even the AI itself is generate for us more attack surface. For example, we can look on the recent hype on MCP servers when we want to connect our cursor or our LLM to a lot of services, and then we need credentials to talk with these services. So probably we take these credentials and put them in our cursor or LLM, not necessarily in a secure way, because we want to do things quickly and not necessarily in the best way in the terms of security. So we are generating like more attack surface. On the right, we can see also, according to our research, some popular services that we found in private repositories in our customer. So for example, we can see Anthropic API key, which is kind of new service, but it's still really popular to have an API key inside code repositories. It's also important to mention that the companies on the right, they're not responsible for the keys, they're not responsible for the securing the keys. It's just common services that people usually use these credentials and usually store them in files in repositories. So when we think about traditional method to detect secret, the first thing come to our mind is to use regex or pattern. So when we rely on regex, it's really hard to maintain them, and also they have a few limitations. For example, they can suffer from high false positive. So we can write a regex that actually can catch a real secret, and it also can catch a secret that is a placeholder or a secret that inside someone put in the word like test or something like that, because it's matched the same pattern. The second thing is the maintenance. So when we have a new secret, we actually need to generate a new regex. Many of the secrets has kind of generic pattern, like 32 characters, like digits or letters. And then the regex involves some keywords, for example, the name of the service that we want to match on. And then if there is a new service we want to catch with the regex, we actually need to write a specific regex, and it's really hard to write the correct regex that not generate a lot of false positive, but also catch the secret that we want. The third thing is the lack of context. So many of the files that contains like a placeholder or test secret, you can find these words inside the file. If you understand the context of the file, you can understand that it's not a real secret, or maybe it's a low confidence secret.
So, like Erez said, the limitation of regex-based detection can be a real headache. Both false positives and false negatives create a lot of noise and sometimes even create embarrassment. Today, the closest thing we have to our critical eyes as security researchers are large language models. On this slide, we can see two examples. And the first example, I don't know if you can read it, it says the variable name there is Java privada, which is in Spanish, private key. So this is an actual example from a public repository. And on the example below, we can see that it's a very generic secret that might be for test purposes. So on the first example, I don't think a regex can actually catch the first example. And on the second example, a regex will catch that example, but it's actually a false positive. So if we're talking about large language models, what are the advantages to using them? It's very clear, but let's talk about them. They work out of the box. The amount of knowledge they hold is often unbelievable. Even with basic prompt engineering, they can perform every task in a very good way. Also, they support very long context length. This is important in our field of problem because I'm sure all of you have seen code files that have more than 1,000 lines. And also, if there's things they don't know or are not familiar with prompt engineering, you can actually fill in the gaps and teach it on the go stuff that it doesn't know. While they have many benefits, they have some challenges, and those challenges are actually specific to our domain of problem. One is scale. We need to scan millions of files a day, and usually the rate limits of external vendors of large language models is around 100 requests per minute. Also cost. Relying on external APIs for heavy workloads can get expensive very quickly, especially when we need high availability and performance. And of course, privacy. Companies are not eager to share their secret sauce with external services, and even if they wanted to, there are some legal regulations that prevent them from doing so. So, do we have to use large language models? How about small language models? So, if you haven't heard about them, small language models are models with significantly lower number of parameters. How lower? Around 8 billion parameters and lower. This is the definition. For comparison, large language models hold around 300 billion parameters and even more. Some examples of such model families is Phi from Microsoft, Qwen from Alibaba, and Llama from Meta. So the challenges we've seen before can actually be handled with the advantages of the small language models. Runtime and performance. We can run them with little memory and with little compute power compared to the bigger brothers. In fact, we can use CPUs to perform inference instead of GPUs. And that leads us to the cost. We can run small language models on standard machines instead of GPUs machines. So this reduces cost significantly. And of course, privacy. The model is ours. It runs in our environment. No data is sent out. So it actually solves all of the compliance issues.
So when we thought how we're gonna solve this problem, and we learned about a small language model, we understood that we want to try it. And the best way is just going to fine-tune a small language model for a specific task to detect secret. So we need to answer a few questions. The first question is which data we want to use. Which data we want to use for training, for evaluation. The second question is what is the truth, or what is the success of the criteria of the success. And the third question is, can we run efficient enough on the CPU machine? So let's start and deep dive and answer those questions. So defining the task is pretty easy. We want to take a language model and fine-tune it to our specific task to detect secret. It means that the model not necessarily will be good in general knowledge, but will be amazing in secret detection. We need also to set a target. So our target was to be able to process a code file in less than 10 seconds on a single thread CPU machine. Also, we want to take advantage of a language model and to perform multiple tasks in a single action. And our task is not just extracting the secret, also categorize the secret and give a confidence. Confidence will help us to understand if the secret is real or maybe it's a test secret or a placeholder, and it's really important for our secret detection engine. So first, we need data, and we didn't have any data. So when I think about this problem, let's say 3 years ago before the LLM, it was really hard to generate good quality data for this problem, because you need a lot of analysts and people go over a lot of code files and label the data, and it can take hours, days, and cost a lot of money. Also, you need a lot of people. And today we have the LLMs, so we decided to automate the process as much as we can and to use multi-agent approach. So we started with a really large data set that is not categorized at all, which is GitHub Archive. It's a project with all the public data from GitHub. Then we use the basic filtering of some basic keywords, and also we filter only the data that we can use for training and evaluation according to the code license. Then we decided to use 2 agents, LLM agent, one of them based on Gemini and the other one based on Sonnet. And we did some mechanism to take the agreement between those agents and merge the results. Also, we used a third LLM to validate the results and validate the confidence with LLM as a judge. We handled some edge cases and did some manual review. All of that we did on a pretty small amount of data until we got to the results that we want. We did some refinement to the prompt, to the confidence, and everything around it. And then we run this process on 100,000 files, and we ended up with data in a high quality that we're happy with the data. And it cost us around $5,000. I know it's not cheap, but we were actually a bit generous with the models and the experiments that we've done. But it's pretty much not expensive according to the data set that we got. We have 100,000 files that we started from all the public code in GitHub that has many, many secrets inside and a lot of them, like a good variation of secrets. So here we can see an example of our labeling. On the left side, you can see a secret that is probably a real secret. Also, it has a category. It's related to Facebook app secret. It's also extracted the variable name and the secret value, and the confidence is high. On the right side, you can see a secret that is probably a placeholder according to the secret value, and the confidence is low as expected. It's also related to tick-tail access token. So the model extracted the description, the category, and also the confidence, which is the most important for us. So for fine-tuning a language model, we define the task of what we want to take a pre-trained model on domain specific, and specialize it to our new task. There is actually two main ways we can do that. The first one is we can do full fine-tuning, which update all the model weights. It's powerful, but it requires a lot of resources, and it's probably really costly to do that. So even for a small language model, they have 1 billion parameters, or 500 million parameters, or 3 billion parameters, and it's a lot of weights to change, and you need like a lot of GPU time to do that. And the second option is parameter efficient fine-tuning. And for example, LoRa, this is the method that we use. That actually you train a small adapter instead of the full model, and it actually can save a lot of compute, and you can do it quickly on a single, for a small language model, you can do it on a single GPU machine. And it actually can take just a few hours, even for a large data set like we had.
So, like Erez said, he talked about two ways of fine-tuning models. We chose with LoRa. LoRa is low-rank adaptation. In simple terms, LoRa fine-tunes models by adding small low-rank parameters to the model, and this dramatically reduces memory usage and compute during the fine-tuning process, making it more efficient and flexible. And by flexible is meaning that we cut the time that we need to fine-tune a model, and by that we can perform many iterations and change the data, change the parameters, and so on. You can imagine it by like imagine the model as a system of lenses, and LoRa is actually adding more filters to the lenses. In the fine-tune process, we actually are trying to figure out what those lenses are. We don't touch the lenses of the original model. Also, we applied quantization. So quantization is a trade-off between accuracy and performance. Basically, it's representing numbers with less numbers. We're going from representing numbers in 32-bit floating points to 8-bit integers. And why is that important? Because a model is a series of mathematical operations. Using smaller numbers makes the operations much faster. We can see like the main stuff that we care about are memory footprint, processing power, and inference speed. After quantization, those numbers get way better, and we don't lose a lot of precision. Also, because as we talked before, we are running at very, very large scales, around 20 million files a day. Each token that the model outputs, the fine-tuned model outputs, is actually time and compute. So we want that the model will output only the necessary data, and only afterwards we will post-process it to our relevant JSON data. So that's how we implemented it. The model outputs a tuple, and afterwards we post-process it into a structured JSON. Once we got the initial results, we defined KPIs around file level and secret level matching. We also had to deal with hallucinations. Sometimes the model output the results that are not exactly in the input. We provide it with a code file, and it outputs variables that are not there, but close. So we actually review the results, and we found the patterns of those hallucinations. It's kind of a closed set of hallucinations. It enabled us to build a custom fuzzy mechanism that we could match secrets and actually get the true results.
So let's talk about the performance metrics. First, for the baseline, let's talk about the regex detection for generic secrets. We're defining generic secrets for secrets that we didn't have a good regex to detect them. Meaning it can be a username and password or some API key that we don't know or don't have like a strong patterns. And actually we try to create like generic regex to detect them. And the results were really, really bad. This is actually how we started the research. For the regex detection, we got 56% of recall and 32% of precision, which is awful. For the LLM, for the small language model that we trained, for example, the 1 billion parameter, we got 82% of recall and 85% of precision. And it took us only 10 seconds per file for processing. And we try even a smaller model, a Quen, and a version, Quen code, in a version of 500 million parameters. And the recall was a bit lower, like 71%, but still the precision is high, 87%. And it took only 2 seconds per file. And those results are for a single GPU on a single thread. Those kind of model can run even on your laptop. And your laptop is actually will be probably faster if you use like a Mac, for example. And it is amazing because if you can run it on the laptop, you can deploy this model, for example, and use it as a pre-commit to your Git or something like that. Thank you. So we're going to finish with some key takeaways, and let's talk about the framework that we use that you might find useful also for you if you tackle this problem and want to fine-tune a small language model. The first framework that we use is Unslosh. It's a framework that actually enables you to run in a very efficient way, fine-tuning for a small language model. It provides you also like step-by-step notebooks, and you can run it even if you're not like a data scientist. And the second framework is Llama CPP. It's really good for inference and when you actually want to go to production. So Llama CPP can help you to quantize the model in various quantization method. It is also provide you a single file that you can load with Llama CPP library. And actually you can run it on a CPU. You can optimize it also for a specific CPUs if you want. And I think we thought it's really good for inference. And some general takeaways and future outlook. So first, small language model. I know you hear a lot about large language model and you use a lot of large language models, but it's not only large language models. So if you have problems that you need to run on scale, for example, or you want to run on an environment that you doesn't necessarily have like a GPU, it can be a good solution for you. You can take a large language model and use it to label data, and then generate a small language model that will be specific for your task.
Also, another important takeaway is AI and security teams should actively use large language models to generate and label data. They should actually integrate it in their research, and they can use this data to train new models, to validate results, and to create more data sets. Also, I think a very important key takeaway here is the advancements of frameworks. If we look at this field of fine-tuning or model training 4, 5, 6 years ago, it was reserved for data scientists. But now, with the ease of use, software engineers, analysts, security researchers can now also do those things. And even now, there are cloud providers that are providing, in one click, fine-tuning a model. Just provide the data and provide the parameters, the cap of the cost, and you will have a fine-tuned model. Thank you for listening. Do you have any questions, maybe from the audience? Yeah.
So what was the precision and recall if you actually test the data on a large language model itself? Like how close do you get to 100%?
So the benchmark was built by large language models. So actually the numbers you've seen, so we tested our regex detectors on the same data set and our fine-tuned models. So we get to 86 precision out of a big model that generate the data. So we're not as a big model, but we're very close in a fraction of the cost and the runtime.
And also important to add that this data set of the large language model we manually reviewed the results and we saw that it's pretty much accurate. We didn't review 100,000 files, but we review like many files and we estimate the accuracy of those results.
Hi. Sorry, what do you mean by recall and precision? Like, how are those numbers different from accuracy and like false positive?
It's
false negative?
recall is the coverage basically, and the precision is just the out of the detections, like the true detections, like the model, like on how the percentage when the models say that it's a secret, what is the percentage is actually a secret.
Okay, thanks.
Was the model more accurate for structured secrets or like well-known prefixes versus like unstructured?
So for the structured and let's call it obvious secrets, it was pretty dead on. I think most of the times it missed, it was for the secrets, the non-obvious secrets. For instance, you define a variable with an unrelated name to a secret, but later on in the code, you use it for authentication, for instance. So the interesting part, it was that the model actually catch some of those secrets, that they don't even look like a secret, but afterwards you use them for authentication. But most of the secrets that he missed were of that kind.
Yes. Also, it was our research focused on those kind of secrets because our secret detection already have a lot of regex that recognize like strong pattern secrets.
Yes, thank you for sharing all this. On one of your slides, when you were showing the confidence score that was produced, so on one it was rated high, on one it was rated low. When I was looking at it, I couldn't really tell as a human looking at it. The one on the right that was low could have very well been a secret. So how does can you speak a little bit to how does the model differentiate? And in that particular case, you showed why one was low and one was high?
I think in the example that I showed, it was just a placeholder. So it was access token underscore XXXXXX. So it's pretty clear it's low. And we defined actually the instruction for the confidence. So we instruct the large language model and we explain what is low and what is high. And also we did some post-processing logic to define the confidence or re-rank the confidence for cases that we believe that's supposed to be like low. So most of the time the large language models was good enough, but we added some post-processing for this to change a bit the confidence, and then we use it for the training.
Hi, good work. My question is, how long did it take you guys to fine-tune the model from start to finish? And also, how do we access your currently built model for like maybe our AppSec workflows, for example?
So the total research process was around between 2 to 3 months because we had a lot of parts in it. You had a part of generating data and then refining it until it's good to a certain point. Then we had like the fine-tune stage and the review stage, and then we went backwards. We actually regenerated the data, then we fine-tune again. But a fine-tune cycle, just fine-tuning the model cycle, is between 8 to 12 hours on a machine with 2 GPUs, for instance. But the whole process actually took almost 2 months because it's a long process. And there's a lot of also reviewing and manual reviewing and going back and forth. So this is like, it was a classic data science, model training, but also it had the part of, it's kind of a hard problem of the secret detection.
Yes, also I can share that we did it like maybe 6 months ago. So we struggled a bit the first time with the frameworks. I think now in those days it's a bit easier. And also, as we said, there is some services that you can use in the cloud provider to fine-tune after you have the data. And I think after the first time that you do it, it's much easier for the next time. For the first time was a bit, took 2-3 months, but next time that we'll have to do that probably will take us, I don't know, 2 weeks.
Very quick follow-up on confidence. So it looks like from what you said, when you trained your model for confidence, you were considered how the secret is structured. Like, for example, XSS or some 1, 2, 3, that probably it's not the real one, right? But I just want to ask you, did you also consider where you found those secrets? For example, you can have 3 configuration file, one is for production, another one for dev, then you would do something about it as well.
Yes, so it's also part of the confidence. So you saw basically the low and the high. There's also like a medium confidence, but we try to instruct the model if the secret looks like a real secret, but it's like, let's say, a test file or an environment file that's not for production, to set it to medium. So we keep the high is probably the production environment and let's say the most sensitive. The medium secret value looks good, and low the secret value looks placeholder or not a secret.
And that is time, folks. Give it up for Danny and Erez. Thanks, guys.